recent work about boson sampling for generalized bosons, and with graduate student Yi and this Dominic Hedinger and Andrea Granking are postdoc, and the affiliation with Maryland and the Joint Constitute and the Quicks, and based on this archive paper. Okay, and so let me just talk about my motivation. So I will quickly review that or spend some time review why is boson sampling and why it is important. And I will also talk about what do we mean by these generalized bosons. And I will talk about this so-called generalized boson sampling, and also some possible implementations. Okay, so motivation is that we know that quantum supremacy definition is that some tasks are easier by using quantum computer than using classical computing. And usually the way to define easier is that in computer science, usually polynomial time, which makes easier, and exponential time means difficult. And so the goal, the general goal for this to prove that quantum computing is actually better than classical is to prove that there are some problems which is indeed in BQP but not in BVP. So this is bounding quantum polynomial time, and this is probability bounded, the classical bounded probability classes. Okay, so most famous example is this Shor's algorithm. Yeah, so this is the standard conjecture that this BQP is outside the P, and but not include all the NP. Okay, and so the other part, the possible answer to this question is also boson sampling using a non-interacting bosons. So I will explain in detail. And also there is a talk that for boson sampling, which is very interesting. Yeah. Okay. So and we will see that the boson sampling, there are two types of boson sampling. They are both corresponding to two different matrices, matrix function, and I think they all come from combinatorics. So yeah, I mean I will explain it in later. Okay, so and can we extend the notion of boson sampling to wider class of system? This is the motivation. Okay, and let me just also say that why boson sampling theoretically is better than Shor's algorithm. We know that Shor's two-factor integer n, right? Shor's algorithm runs polynomial log n, so this is more precise. But the most efficient classical algorithm is called number theory sieve, is exponential in n. I think everybody knows this. And there are two disadvantages of this Shor's algorithm. The first one is theoretically. I mean, if someday there is a people prove that there is a classical algorithm that runs in polynomial time to solve this integer n, then nothing happens. So what do I mean? Nothing happens means that there is no theoretical foundation will be break. Like for example, most of people believe p do not equal to np, but if there is a classical algorithm that solves this, that can solve factor this integer in the polynomial time, that will not break some consensus that the computer scientists believe. And also experimentally is that in order to do this Shor's algorithm, one need to do the quantum Fourier transformation, which is needs for quantum computing. Okay, so let me quickly introduce the standard boson sampling. So we know that there's a two matrix function, right? One is called permanent, one is determinant for 2x2 matrices. For determinant is A, B, C, D, AD minus BC. For permanent, just AD plus BC. Okay, so for permanent is this, and then for determinant is, so the only difference is that you take all the minus sign in the matrix, and you take all the minus sign in the determinants and change it to the plus sign. Okay. So determinant is linear algebraic, easy to compute, and corresponding to volume of spanning vectors. Okay, and there is an easy way to quick algorithm to compute it, so the Gaussian elimination. But basically, you just times the first row up to some number and kill the first element in the second row, and you keep doing it. And this permanent is combinatorics, and also it seems like that we need, in order to compute permanent, it seems like we need to compute that almost n factorial term. Okay, and the people in the 1970 proved that this is called Sharpie complete. Yeah, so Sharpie complete means that it's much difficult than NP complete. So NP complete is asked whether given a combinatorics problem like 3 set, and you answer whether there is a solution or not. But Sharpie complete means that somebody gives you a B complete problem, and you need to tell him the number of the solutions. Okay, so let me just quickly say, yeah, this is just a simple example that you can see that if you start from determinant A, D, B, C, the permanent, if you do the Gauss, if you add the K, add the second column with the some constant k add on the first one, you can see the determinant still don't change, right? But if you do the permanent, it change. So this means that the determinant can easily using a Gaussian elimination to do the computation, but for permanent, it's not. Okay, so yeah, this is just some intuition of why permanent is interesting. Yeah, also you can watch Scarris's video. This is very interesting. Okay, so so it's natural. So it's why how permanent did appear in quantum mechanics, right? So if someone, let's do some very simple example. So if there's a quantum circuit, right, with two mode, and this is photon, and the more precise is that you do this. So you do the mode transformation on this creation and integration operator, and your psi will become like huge. Will become this. So you just do the mode transformation on the creation operator, and then you can expand it. And then you ask what is the probability that you measure 2, 0 here, and you can see that it's just 2 lambda 1 square, lambda 1 2 square, and you can write it as permanent. Okay, and for 0 2 you arrive another permanent. For 1 1 you arrive another permanent. Okay, so this is why permanent naturally appear in quantum mechanics in the photonic system. Basically, you just come up with, you just plug in some photon mode, and then you random, and then you do some unitary, which this unitary is freely rotate this mode, and you will get some information about this unitary, and but the probability will proportional permanent. And as we show that permanent in computer science is hard to compute, so this gives us some intuition why Boson sampling should be a hard problem for the classical one. Okay, so permanent naturally show up in the quantum optical system. Yeah, so the general one is that if somebody gives you L, somebody gives you K, then the probability of KL will be some permanence corresponding to you take some rows in the matrices of lambda, and you compute the probability. Okay. So this is just general rotation. General notation. Just you take K1, K2, K3, L1. This is the notation. Okay. And yeah, so yeah, this is the general proof. I put in here just to want to compare to the future. Yeah, so then you will know why I put in here. Yeah, so basically the proof just expanded everything you know and using a weird identity, and you can show that finally become the permanent. Okay, and you can see that this proof has no physics, just combinatorics. So the idea is that you just expand it every A, and you just do a rotation, and then you check that whether this, you use this identity. So this identity will give you some permanence. Okay. Okay, so so the results that the so-called the task so-called exact boson sampling means that given a unitary description and the input style 1, you want to have some classical algorithm which output a probability distribution. Okay, and then there's an approximate version is that you output a probability distribution that close to the original probability in total variable distance. Okay, so I think I don't need to show this, but I just very quick. So what do we mean by the approximate probability distribution, right? So for example, if you don't know how to calculate the binomial coefficient, then you can just building this machine, right? And you just count how many stands you have, then this is you can approximate the binomial distribution. So in this case, is that it's exactly the same as Boson sampling. We're using photonics and try to build the probability distribution proportional to permanence of the matrix square. Okay, so yeah, it's just this is called the Galton's board. Yeah. Okay. Okay, so the take-home message is that under certain complexity assumption in computer science, some conjecture in combinatorics, they are widely believed in true. The exact and approximate Boson sampling is hard in average. So hard in average means that if you randomly choose the unitary from this technical terminology is called hard measure. Okay, you take because unitary forms a Lie group, compact Lie group. Okay, so every compact Lie group has some so-called hard measure, and you use this hard random. You take matrices randomly, and average is hard. In average, this exact and approximate Boson sampling is hard. Okay, so namely is that there's no classical algorithm that can solve it in polynomial time. Okay, and this is the proving strategy that proved by Aronson. So the idea is that you need to use two conjecture, which is most of people believe it's true, but they cannot prove it. Okay. And finally, you can use toe-dot theorem. So the idea is that yeah, this is why Boson sampling has more theoretical foundation as Shor's algorithm. Because if one can solve this problem in there is a polynomial time classical algorithm, and you can solve it, then you will break this, and you will prove that polynomial hierarchy collapse in the third level, because you can prove that BPP to NP it will be in the another. You can use toe-dot theorem, so you will show that this polynomial hierarchy will collapse. So basically means that Boson sampling has stronger theoretical foundation compared to Shor's algorithm. Okay. And let me this is just quick review about this polynomial hierarchy. So we know that there is a P, you can create NP and co-NP, and you can use the oracle to define a P to NP, and you just keep going. Okay. So the conjecture in computer science is that every complexity class are different. So these are different. And you can prove that if let's say this level that these two are the same, then every higher one will collapse into this level. So the simplest one is P to NP, although people cannot prove it. Okay. Okay, so most important question in theory is just P. So one can construct infinite family complexity class. So all of them are called the polynomial hierarchy. So this is usually when this quantum complexity guy always told that if you prove something that complexity class will collapse into, this is the first level, second level, third level. Okay, the fact is that once a level collapse, then all above collapse. Okay, and every class is different from each other. There is conjecture, and Ph is not the same as BQP. So all these are Ph. Okay, so the Boson sampling just say that if the Boson sampling can be solved classically, then all of this will collapse into here. Okay, so let me just talk about another one called the Gaussian Boson sampling. So this one is the usual experiments people will do. Okay, so this the idea why Boson sample idea why people using this Gaussian Boson sampling. Oh, sorry, this is AU. Yeah, sorry. Is that the simple photon state is hard to prepare in the experiments, right? So in the previous step, we need to do the Fock space. We need to do the 1, 1, 1, 0, 0, 0, that kind of states as our input state. But the Gaussian state is easier to prepare and natural. And so one idea is that you can ask what's complexity if we use a Gaussian state. Okay, so let me just describe a little bit. So this is usual definition, right? It's alpha is usual. This is coherent state. And one can, given a quantum state rho, one can compute this so-called Q function. And the one special, this is definition. So when people say Gaussian state, means that this Q is it can be expressed as Gaussian. So it's Gaussian it's quadratic in alpha, and there's a covariant matrix lambda sigma here. Okay, so standard state, which is one is coherent, one is squeeze state, one is thermal state. Okay. And so let me just talk about example. So yeah, this is definition. So as I say that there's a rho, right? And if somebody give you a rho, then you can try to compute this inner products. If it's sigma, if it's quadratic in the alpha, then you can write this. This then is called Gaussian state. So one is the so-called single mode squeezing. You do some squeezing operator, which looks like this, and echelon of vacuum. And you can write down as something if you represent this squeeze operator is this R times exponential I phi. And you can check that if you plug in this, you will get exactly the same. You will get this quadratic. Okay, and there is a so-called two mode squeezing, and then you can also check it will give you a Gaussian state. Okay, so previously we say there is a function called permanent, right? And there's another function called Hafenian. So the Hafenian definition is that if there is a n by n symmetric matrices, and you can define Hafenian to be the I and J and the product, and then there is a so-called perfect matching. This is hard to understand, but let me just provide example. So when n equals to 4, you have the perfect match in 4 is just 0, 1, 2, 2, 3, 0, 2. So it's like you given two nodes, and for every two nodes, you find a pair. Okay, and each node must be paired with another, and they cannot share the same nodes. Okay, so in this case, you have 3 of them, and your Hafnian of the B matrix is B, just defined to be B0, B23, B0, to just copy the indices. Okay, and there's a strange identity called that the permanent A is just Hafnian of 0, A transpose 0. So this gives you a feeling that if the permanence is, if you have a proof that based on a permanent is hard to compute, maybe you can translate it into the Hafnian is hard to compute. So it's like if one can compute Hafnian easily, then one should be able to compute permanent easily. I mean, yeah, because there is an identity rule, right? So if there's a machine that you can compute Hafnian easily, you can actually calculate its permanent. Okay, so the problem is that why this Hafnian show up? Okay, so let me just provide a quick example that how this Hafnian come from, right? So if you have a matrix F, you do this exponential aij xij. These xij are some independent variable, and you do the differentiation with respect to x1, x2, and you take x to 0. You can check that it gives you a12 and a21. If you do the 4 of them, and you take x to be 0, and you get this. And if you assume that A is symmetric, you get a12, a34, a13, a24, a23, a14. Okay, so you can see that this Hafnian really come from when you have some quadratic term in xij, and you do some differentiation, and you take x to be 0, and you assume A is symmetric, then this Hafnian it actually appears in this calculation. I mean, and also if you're interested in if you know some quantum field theory like high energy or something, you know there's a guy called Wick theorem. If you want to compute the correlation of some free, you want to Feynman diagram, and you can see that your four free theory correlator will give you the same contraction. So it's like 1, 2, 3, 4, 1, 2, 3. See that this is just some analog, but you can prove that they are actually come from the same reason, that if you have exponential quadratic, and you can do this. Okay, so yeah, this is just in general. If you have this kind of variable, alpha 1 of m, and the stars alpha 2 m star of m star and transpose, and if you do this kind of thing, you do like partial 2 to the n to some exponential quadratic in alpha, and you can prove that there's a French, this is some combinatorics difficult formula. You can prove that it will give you some Hafnian of these original matrices. Okay, so why I talk about this? Because let me just do this. Let me just do this. Yeah, so let's okay, I should start from here. Okay, let me just yeah. So the idea is that the Gaussian bone sampling starting point is that somebody give you the single mode squeezing, right? And so previously it's Fock space, right? And then so now you do a single mode squeezing, and you apply the same unitary, and you try to measure the output, but restricted output to be 0 to 1. So this will give you some matrices S. Also give you a sigma. So this sigma is just the Gaussian. Remember that Q will give original has some sigma. And this is the result sigma. This is the yeah. You can show that the result is Hafnian. Yeah. So I should start from here, right? So the idea is that the probability in photonics or in the coherent state basis, there is a formula come from this. And suppose your density state rho has this Q representation, and you want to measure that. You want to ask what's the probability that you get 0, 1, or 1, 0, or some string, and you can calculate. There's a p function where here, and you can just plug these two into this, and this delta, do a change of variable. Now the delta function will give you this delta function, when you do a change of variable, will be the differentiation act on this original act on the quadratic form. Okay, so by using the previous formula, that you will get Hafnian. Okay, so this is why this is just the quick derivation that why we can get half-union. So basically you will get this, and then there's a matrix A. This A is defined to be some identity matrices minus original sigma. Okay, so you will get the half-union of the results. You'll get the probability proportional to half-union of the original matrices. Okay, so this is the other setting called Gaussian Boson sampling, as I just showed. So the probability to measure n1, n2 up to nn where proportional some matrices as some matrix, and you take half-union. So this is almost the same as permanent, right? Just from the previous, the standard boson sampling give you the permanent, but this Gaussian one give you half-union. Okay, so this is also two more squeezing. Okay, and the experiment usually do the Gaussian. Okay, so usually linear boson sampling called ABS, and for Gaussian boson sampling we call GBS. Okay, so let me just recap. So for linear boson sampling, we have the permanence, right? Well, our probability just for permanence. So linear boson sampling by using a single photon state will give you a permanence square. And for the Gaussian boson sampling, will give you half-union. Okay. And there's a reason a paper proved that theoretical proof that the Gaussian boson sampling is theoretically difficult. Okay, but if you go back to see this proof, then you will see that why somebody give you permanent half-union is not related to physics, right? The original permanent comes from this identity. So it's like so the idea is this: if you have a system which is somehow like you can make this identity emerge in your system, then your system should have the similar quantum supremacy as the photonics. So this proof do not related to physics. It's just some mathematical identity that give you the permanence. So this is our motivation. Okay, so this just provides some background. And then you want to ask where half-union come from? It's come from this strange inequality. A strange identity. It's like you do some differentiation on the quadratic term, and then restitute someone to 0, then you will get half-union. So this makes people to think. This make me to think why the permanent half-union are why photonics are important in this derivation. Okay. Okay, so this is just some detour for some guy who are interested in like doing some mathematical physics. There's a determinant half-union something, and there is some matrix function. They are all related. Yeah, and there are also some more exotic one that if you're interested, you can check out. By the way, so if one knows some condensed matrix, you know there is a guy called Pfaff-Yen. Pfaff-Yen square is determined, and the permanent are also related to half-union. Okay, so now come from our main motivation. How come from our main results? Sorry about this, because I want to talk about some basic backgrounds. Okay, so generalized bosons. Let me just talk about what is definition of regular boson, right? And the definition of regular boson is like for each site you have a correlation and adhesion operator, and their AI AJ Dagger commutator will be delta IJ. And for each site, for different sites, they are all commute. Okay, let's suppose that we cross this we forget about this condition. Okay, and then he asks whether there's a particle only has this configure, only has this requirement, not this. Okay. So we can define like more general one. We can say that our BI and BJ Dagger is not delta IJ, but for some special number, some special, it's not identity matrices, it's some other matrices, but for different sites still commute. Okay, and you might think that, oh, this is just some weird mathematical, I mean, some strange generalization, right? Someone who doesn't know any physics just try to somebody gives you this and just try to come up with some strange thing. Yeah, but it's not like this is not like crazy mathematical generalization. By the way, because there are other particles which has this property. For example, if you do this is a standard boson, there is a guy called boson pair in the quantum circuit. So the cavity QED, you can define B to be A squared. This is usual. You can view this as another particle, and one can do a spin as bosons. One can view spin as bosons. And then there's a guy called Q bosons. There are the M-pair bosons. So these are all bosons. There are bosons in the sense that for different mode, they're actually commutes, but they're single size operator. There are BI and there are BJ Dagger for single size. It's not delta function. Okay. By the way, so this f of n, we define this b Dagger n0 to be f of n n. So for the people who know the photonics well, right? There's some quantum mechanics. This is square root of n factorial for the square root of n factorial for the photon. And one can also divide the multi-mode by just doing the same thing as the general photon. I mean, as the photon. Okay, so we call f of n as bosonic factor, which is complete determinant algebra. And then these are some examples. So as I said, this is standard boson, which f of n is the square root of n factorial as you learn the quantum mechanics. For the boson pair, you can have some different one. And also for spin, this is, I think everyone knows it, right? This is just the spin SU2 algebra, okay? And then for Q boson, which is shown in high energy physics, will give you some strange f of n. This is called the Pohammer symbol. And for M-pair boson, this M-pair boson is recently found in the experiments. It's like an exotic boson that you can find in the experiments. Okay. Yeah, so they all have different f of n. Okay, so now what's the question? Obviously. So what if you do the boson sampling on these generalized bosons, right? So because previous people do the photon, so the natural question is asked, what if you do the boson sampling on using these different kind of species? They have the similar property as bosons, but somehow they are a little bit different. Do they give you the same complexity or same permanent function? How about if you try to do the Gaussian boson sampling on these generalized bosons? Yeah, the answer is yes. It's for this is yes, but under certain assumptions. Okay. Okay, so let me just recap how permanence. You start from all 0, and you do this. You do this mode transformation. Okay, and you expanded all the mode transformation. Then all you need to do is just using some strange identity to group everything of this. Then you get the permanence. Okay, so this is the standard proof in the photonics. This is why you can arrive the permanence. Okay. If you do a general one, right, you can start to do the same thing, but just replace this original f 1 over square root of n factorial to be 1 over f of n. So the only difference is just this, okay? And you can do the linear mode transformation, and you expand it. You will find that, oh, I get exactly the same expression as previous did. Then I can still using, so this is the coefficient that I arrive. Then I can also use the same identity. Okay, so this is the miracle. This is the important thing happen, right? So, so it looks, so now we do different. We don't do photon, right? But do some other species of bosons, or some other kind of particle, which is the similar bosonic algebra. Then we can still use this identity and still arrive the permanence. Okay, and the amazing that is very simple calculation is that if you choose f of n to be square root of n factorial, then you can see that if you do calculation, you will arrive the same boson. You will arrive the photonic results. You get 1 over n factorial I from 1 to n. This is exactly the same as the boson calculation. Okay, so I just quickly show that the proof of argument results. Okay, so the idea is that consider a linear mode lambda of u of m for m modes of generalized bosonic algebra on those modes with bosonic factor f. Then the probability of measure k is a vector given a Fock space input state I is given by this. Same complexity. This proof is not easy as you think, because even though you arrive this equation, you still need to go back to the original Skyrison's paper about generalized boson sampling and check that whether about boson sampling, check that whether this factor change will give you the different complexity argument. So it's not so simple that what I want to say is that it's not so simple that even though you derive this probability distribution well proportional to permanent square it's not necessarily guaranteed that you get the same complexity hierarchy collapse argument as simple as bosons. So you need to check all the details to check that if you change this coefficient, change that coefficient in the original Skyrenson's paper, that you will still arrive the same complexity argument. Yeah, so this is I only show the first part in our in this presentation. And the rest detail that if you want to really prove that these factors don't change your hierarchy collapse argument, you need to do some detailed analysis. Yeah, but basically this is the first step. You arrive the probability is proportional to is the same as boson, you get the permanent square. Okay, now you can ask the same thing for Gaussian boson sampling, right? As previous we did in a photon. Right? We can ask the same question. Okay, but now here comes the problem, right? Because in the photonics, you have so-called coherent state, but in this generalized boson, maybe we don't have coherent state. So maybe you need to define your own coherent state, and then you need to define your Gaussian. Okay, and so our idea is that if you have so-called Gaussian Q function with no first moment, then we can show that you still get Hafnian. Okay, so let me explain in detail. Okay, so in the photon case that we have this f of n equals to square root of n factorials, and then we have so-called normalization. Okay, so we can take, yeah, this is just normalization of coherent state. You get exponential alpha squared, and then you define your so-called coherent states. Coherent states is just defined to be the eigenstates of the anti-deviation operator. So you have, this is your coherent state. And normalization, yeah, I mean, that's the same thing. And then you can define a so-called P function. So this P function is just some calculation, yeah, so this f of n is square root of n factorial squared. Yeah, so you get 1 over n or something. Yeah, so one can do the parallel analysis on these generalized bosons. For square root of n factorial, we just replace by arbitrary function f of n. And then we can also do a normalization, right? F of n squared, alpha to n, divided by n factorial, and from 0 to infinity. And then we can also define our coherent state. Okay, so our coherent state is almost the same as this coherent state. But if you replace this f of n to be square root of n factorial, then you will see that they are two the same. They are exactly the same. And then you can also define a normalization. If you replace this f of n to be square root of n factorial, then you will get exponential. You will see that these two are also the same. Okay, so basically it's like mathematically one can parallel all the photonics machinery to these generalized bosons and define your own coherent state. Okay, and it seems like you have many ways to define it, but there's one way that I think we believe this is the good way to compare to the photons. Okay, so let me explain why is P function. Yeah, I mean this P function defined to this. Okay, so if you do the integration on this alpha and you plug your P function definition, and you expand it, and do the change and do the integration by parts, and you will check that this final result will give you the number operator. So this is why this P function is called P. This is why these P functions are important, because if you do the integration on alpha of B, you get the Sn. Okay, just a sanity check that our definition of this P function is not so crazy. Okay, so let me just recap the standard Gaussian boson sampling. You do some single mode squeezing. This will give you some S originally, and you will get some mode transformation. So these are large unitary called T, and you can your sigma will be this. Oh, so there's a thing that I also want to mention, that if this T is identity, you can check that if this T is identity, then you will get back the same as this. You will get the same thing of S as Dagger. Okay, and you want to measure, and the probability that you get, you just take the Q times P and do the integration, and then you will get the trace. you will get the expectation value. So as we said, you just plug your Q and plug your P, and do integration, you'll get probability. And as we prove that if you do this type of thing, you will arrive some differentiation on the quadratic on exponential, and this will mathematically naturally give you Hafnian. If you restricted Ni to be 0, 1, then you will arrive the Hafnian of some matrices AS, which related to this sigma. Okay, and so this give you the quantum supremacy, because we believe that Hafnian is higher compute. Okay, but this AS is just the identity matrices minus this sigma. So every mode, if your mode is very complicated enough, then your sigma will be complicated enough. Then your A will be complicated enough, and compute the Hafnian of A will in general be difficult. Okay, so this is the standard Gaussian bond sampling. Okay, so we can do the same thing, right? We now can do the same trick. So this is our theorem. So given the bosonic dagger and f of n, suppose we have a Gaussian state of generalized bosons, and this Gaussian bond sampling output is still Hafnian. Okay, so what I want to say is that if we do our generalized bosons calculation, and we will still get Hafnian. The only difference is that there is a coefficient. There is a different coefficient called C1I, and this C1I will depend on property of generalized bosons. Yeah, so let me just do the proof sketch. So the idea is that we have this P function, right? This is for a generalized P. So this is our generalized boson, generalized bosons. We have our P. So the only thing different is that in the boson, in the photon case, this n of alpha is exponential alpha squared. So you will get the quadratic. You will get this. You will get like exponential something. But in this case, in general case, that you only get some. You will only get some function n of alpha, which is not exponential, and you get this P. Okay, so this is our serious assumption is that we assume that there is a rho such that in a generalized boson case, we still get Q. We still have this Gaussian Q. Okay, and now we can calculate probability by just product this and do the differentiation. Okay, so this is the results. You just times these two and then do a differentiation, and this delta function will be change your variable. Integration by parts. You will arrive this, and then you will restrict this alpha to be 0. Okay. Now you can do like the Taylor expansion on this normalization. You get C0, C1, C2, and you plug it in back into your expression. You get this. And since we only work on 0, 1, so we only restricted our Ni to 0, 1. So this is important because we only restricted 0 to 1. So when we do a differentiation respect to this term, there's the higher order term alpha 4, alpha 6, this higher term will not get differentiated. If they get differentiated when plugged to alpha, then become 0. So this is the trick that if we restrict it only 0 to 1, then we can just simply take this quadratic term in this inside this expression. So we can just replace this long and alpha to be only take out the quadratic C1 alpha squared. Okay, and then once you arrive this, then you can see that these two terms, they combine into the quadratic term alpha, right? They combine into quadratic term alpha. Originally it has the higher order term, but now it contains the quadratic term alpha. So this will give you the Hafnian. Okay, so it's like the interesting trick. Okay, so if you restrict it to 0, 1, then you can still get results, which is some constant and proportional to Hafnian. Okay, and in this case, this AS looking like this. So this don't care about this M. This just C1I just for a different mode. Okay, and now you can check the interesting. If you plug your original photon, your N of alpha is just exponential alpha squared. So if you do this expansion, you get alpha squared, right, equals to 0, 1, alpha square 0. So when you do n of alpha to be exponential alpha square, you will arrive that C1 is 1. Okay, if you plug C1 is 1, you get identity, which is exactly the same as this identity, right? So which means that you recover the original Gaussian boson sample. Okay, so the proof is, yeah, this is just proof sketch, but the idea is that you understand why Hafenian come from, and you can do something similar to it, and you still get Hafenian. Okay, and you can easily recover original boson sample. Okay, and one can show that in the original Gaussian boson sampling that somebody can also consider the states which has a displacement. So it's like the same as your standard Gaussian the standard Gaussian distribution, right? You can have non-zero mu and non-zero sigma. So you have the non-zero first moment and second moment. So in the photonic case, you can also do the same thing. You can also assume your state is Gaussian, but with the non-zero displacement. And the original people proved that if you do this, you will still get a lot of Hafenian. So your results will be cumbersome, but some Hafenian, many Hafenian sum. Okay. And we can also do our same calculation for general one. So you can assume that you're this, and you plug in general, and you will get something more cumbersome. But you can see the result is still the sum of Hafenian. Then you can do the same argument to prove that if you results still get Hafenian, then how do you argue that this complexity consequence still follows? This needs more work, but I think everything is in our paper. So if you're interested, you can read how to argue that this Hafenian will also give you the results. Okay. And the final thing I want to say is this implementation of generalized linear Boson sampling. So the question is that how do you do the implementation of these generalized bosons? Okay, because previously, okay, so remember previously is that we do photonics, right? In the photonics, that one can use one have the beam splitter and some device which can easily do the mode transformation. But imagine that in some universe, somebody give you this generalized bosons, then you may not have that unitary mode mixing unitary such that you can allow you to do this generalized linear Boson sample. So this is like an interesting trick which comes from this Peraberdus and Arsberg-Kruzik in 2017. What they prove is that what they have shown is that suppose somebody give you the boson sampling Hamiltonian defined to be this. So you have the in and out mode, and there's a unitary matrices are here. And you start with some state 0, and which is for in mode they're all 1, for out mode they're all 0. So it's like you just do these states and then you plug in this Hamiltonian and do the evolution. So after pi over time, you will get something like this. Okay, and amazingly is that one can easily translate this language into the generalized boson. So suppose I do exactly the same thing. I just mathematically replace this A to B. So this B are our generalized boson operator. So notice that now this B and B dagger, they will not become identity. They are different. And we start from the same state. This 1, 1, 1. So this 1 now is the excitation in the generalized boson. And we do the same thing, right? So we can, okay. And after that, we measure it. Okay, so what Peraberdus showed that for spin half system in the dilute limit. So dilute limit means that the number of modes m almost n4 squared. This is the same as in the usual photonic case. We need to assume that the number of we need to make sure that you can easily if you only need the square roots of n people, like for example square root of 365, almost 23 people, that you will have the constant probability that 2 of them has the same birthday. So this is why standard usually in this Boson sampling you don't want the birthday paradox happens. So this is why you need M to be large enough. So this guy showed that for spin half system, if your M mode is proportional to n to the fourth, then these schemes, this generalized boson, one can show that these generalized boson schemes will go as zeros. So their variational distance will go through the as n squared divided by square root n. This is a technical term. So basically, simply speaking, is that if you do this for the generalized bosons or any kind of bosons, then you can prove that this is essentially the same as boson sampling. And the arrow, the variational distance arrows goes as this. Okay. So now we can do some real experiments, right? We can implement circuit QED. So circuit Q and the ion trap. Okay. So circuit QED is that we can in circuit QED we can say that our boson is not the standard boson. We do the boson pair. Okay. So we can define B to be A squared. So that means we can do the quantum supremacy experiments on the circuit QED because we can using our general linear boson sampling and we mathematically prove that this is also has the same complexity and the same consequence in the generalized and as the original boson sampling. And we can also do the ion trap. In the ion trap, that one can define as one can do a super spin, right? Because for each ion, it's just a spin half. If you do like n of spin half, you can get n divided by 2 larger. It's called super spins, just standard quantum mechanics. Okay, so idea is what I just showed. In the spin case, in the ion trap case, you just split into 2, and you do you can shine a laser on this, and you create a coupling, and you create using the previous implementation. And then for cavity QED, you can also do the same thing. In cavity QED, there's a thing called cavity bus, which you can control all these superconducting qubits. So it's amazingly that you can also get permanent in the superconducting qubits if you using this boson pair as your new bosons. Okay, yeah. So let me just about conclusion. Okay, so we have proved that in the general boson sampling setting, which is different from our boson but not so different, we can still have the permanent Hafnian. So the complexity is still there. So one can show that the quantum supremacy is not just based on the quantum optics, right? Because not previously people only do quantum optics, but what we show is that these quantum optics, this proof skill, this interesting identity, not just show up in the quantum optics, but can show up in other kind of platforms. Okay, and we also propose the experiments by using spins and circuit QED. Actually, our experiments can work for all other strange bosons, but in the real world, or maybe the condensed matter physicists or AMO physicists, or however somebody do experiments, maybe spins and circuit QED or superconducting qubits are really that one can actually do. Okay, there are possible future to working on. And this is the first question, what about it? And also one can ask this is more interesting question called non-Gaussian state complexity. So you can imagine that you don't start from Gaussian states, right? You start from some other strange quantum states. Then what matrix function you will get? You will not get permanent. You will not get Hafnian. You will get something strange, different. You will get something strange, different states. Different matrix function. And you can ask what is the complexity of such a matrix function. And there's an idea called stair rank. I don't know, maybe Sarah, maybe if you're interested, you can check this. So there's a way called stair rank classification for the photonics. You can ask whether there's a thing in the generalized bosons. So you can try to using the same technique, ask, where there's more quantum supremacy task you can have. And then there's a connection to the random circuit sampling, right? Usually random circuit. Nowadays, random circuit sampling is like the other quantum supremacy task, and probably become famous, more famous than the boson sample. Okay, and the sixth is what I also very interesting is that if you go to that mathematical literature, condensed matter literature, you can see that there's more exotic functions. So for fermionion and imminence, there are many strange matrix functions, and the mathematician and the computer science already prove all these functions are also hard to compute. So they have the same complexity as permanence. They are all both sharply complete. So that means somehow like if you can do the sampling on this, if you can create something really weird experimental setup, and you can, if your measure probability is proportional to all these really strange functions, then you can create a bunch of you can create a whole universe of the Boson quantum supremacy task, and you can just using all the techniques that people spend a lot of time try to derive from the permanence and go into all these strange functions. So all these, there are more exotic metric functions. There are connection to the condensed matter and mathematical physics. Yeah. So finally, it's 1 hour. Yeah, it's almost. Yeah. So thanks for my collaborator, Ijashi and Dominic, and yeah, also my professor, my supervisor. Yeah, and this is a paper. If you're interested, if you have any question, then you can ask me, or if you want to know more details. Okay. Thanks. Thanks.
Thank you. Is there any questions from the audience?
I may have some questions.
Okay.
First is about the occupation number Ni, small Ni. Why you only choose the Ni to be 0 and 1? Because I think this is boson, so the particle number should be
yeah. Sure. Yeah, exactly. But but this is like the standard. This is in the original boson sampling. Sorry, in the original paper in the Gaussian boson sampling. In order to get the Hafenian, you need to restrict it 0 to 1. So you can simply say that this 0 to 1 is just people try to prove the. Okay, so there are two answers. The first answer is that in order to easily for somebody to prove the quantum supremacy, you need to restrict it 0 or 1. That so you can get this Hafenian. And yeah, this is the first answer. The second answer is that it's like you have the same thing as the birthday paradox. So it's like if your M is very large, then you can prove that the probability of two photons to sit in the same mode is 0. It's almost 0. So yeah, so this is the why usually people only interested in 0 or 1. Yeah, and the third answer is that as I just show it. If you don't do the 0 1, that you will not get Hafenian, and this photon will have different behavior as other photons. So one can simply say, or one can just say that Hafenian is the first order approximation for this Gaussian boson sampling. Yeah. So I mean, I would say that this just some proof strategy that what, or simply is the case, or maybe or also in experiments that as I say that you can prove that M is large. If M is so large that the probability that two photons sit inside here will be very small. Yeah.
So you mean physically you are justified that you are only limited?
Yeah. This is I mean, I think mathematically one can prove this. You using the birthday paradox. So prove that only 0 and 1 matters. So 0 and 1 will contribute a lot of probability already. So yeah, so you need to. So in the experiments, I think you need to do the post selection. If you see this is 2, you need to discard these results. So if you get two, for example, if you do experiments and you get 2 0 0 0, and you need to throw out this and then only do the post selection, then your probability will really become still proportional half.
So if you do the post selection, will that change the probability or it's
okay? Yeah, you will change your probability, but probability is still proportional to the half. You just change the normalization.
Okay.
Yeah. So this is like I think this is what this is the usually, this is I think the usually people doing this Gaussian boson sample.
But I'm just curious, in the formula, the n1 or n2 factorial, if n1, n2 is all 0 or 1, they are all equal to 1, right?
Yeah. But what you're saying, So this is should be there should be all 1. Yeah, sorry about it. They should be all. I think they should be all 1. But I'm pretty sure that if you do the, I'm pretty sure that if you allow this to be 0 or to be not just 0 or 1, you will get something cannot be written as the Hafezi. This is called I think there is a thing which, if you're interested, I think there is a thing called which is called the loop Hafezi. If you're there's some people doing this kind of thing. If you don't do the you can check that it's like when you do a differentiation, you will create an edge connecting 2 points, right? So if you do something, do the 0, 2, or maybe higher than 2, you will get some other function called loop Hafezi. Right? For this is Hafezi part, right? And you will get higher combination. You'll get higher combination of this B if you do the higher calculation. If you do you can try that if you do 0 or 2 and do the differentiation, do the same calculation, you'll get higher. You will get so now your results will not be linear, will not be homogeneous. Right? You will get the degree 2B or 3B or higher B. Maybe there are 4B. So I think there's a paper that I think what you're saying is also correct. There's a paper also proof that this loop Hafezi has the same complexity as the Hafezi. If is that or I think I can find a paper, but basically what I'm saying is that yes, if you do the higher mode, you get loop Hafezi, then you still get the same complexity, or at least people still believe that this is quantum supremacy. But the problem is that in our derivation, if we don't allow 0 to 1, then we cannot prove. Then our results will not lead to loop Hafezi. But for the photon case, you will lead to this loop Hafezi. So basically, I mean, if you're interested, you can check out this. I think I also interested in this kind of thing, but very hard to. It's become very difficult to track. So but
Thank you. I have another question about
sure.
In the Hamiltonian implementation, you also mentioned the large N dilute limit, right? So large N M, and you're trying to argue that in the Fermi's norm, the initial state is close to what? Well, what's the purpose you want to prove in the asymptotic limit? Or why you talk about the closeness in Fermi's norm, or
okay. The idea is that so let me just connect it to my connecting to my pen so that I can write something. Okay, so I think so. What this guy shows is that so what this guy shows is that how should I okay. Okay, so what this guy let me just do this. So what this guy shows is that if you replace maybe let me just do this.